Okay, two things. One, my throat is sore from allergies, so I apologize. Two, I am at school, so there may be other noises around that I cannot avoid, and I apologize for that as well. I'm going to finish the 9.3 notes, so I'm going to finish up with solubility of solutes, in particular solvents. So I finished covering ionic solutes in polar solvents like water, so ionic compounds in water. So now we're going to talk about alcohols in water. So alcohols are hydrocarbons. I'm going to show you a picture of this. They have carbon and hydrogen, and at one end of an alcohol, you will have a hydroxyl group, an OH group, and that OH group is polar, and it can also form a hydrogen bonds with other alcohol molecules, or it can form hydrogen bonds with water. The rest of the alcohol, the hydrocarbon chain, which is hydrogen and carbon, is non-polar, okay? So the extent to which an alcohol dissolves in water honestly depends on how long is that hydrocarbon chain, because there's only one little part of the alcohol that can be attracted to water through hydrogen bonding and thus result in dissolving and miscibility with water. The longer the alcohol hydrocarbon chain gets, the less soluble it becomes. So let me show you what this looks like. Okay, so in this molecule here, this is butanol. The hydrocarbon chain is non-polar, and then at the very end of this molecule, you have an OH group, a hydroxyl group. And that hydroxyl group makes one end of the alcohol polar. The other end is non-polar. So if you dissolve alcohol in water, then the OH group of the alcohol can be attracted to hydrogens of adjacent water molecules, so hydrogens of water molecules that are surrounding this group. And the hydrogen of the OH group can be attracted to the oxygen of water. So you can get hydrogen bonding there. But in the rest of the molecule, you cannot have hydrogen bonding. So the longer this alkyl chain, the longer the hydrocarbon chain becomes, the more it will mask this OH group and the less hydrogen bonding that will happen. So longer alcohols are less likely to be soluble in water because their London dispersion forces, their non-polar interactions, will take over and mask the polar interactions that result in hydrogen bonding. And what you can see, so math means one carbon, F is 2, prop is 3, but is 4, so on and so forth. So as you add more carbons to an alcohol, its solubility, and miscible means that two liquids are soluble in each other. So when it says miscible, it means soluble. As you add carbons, the solubility of the alcohol in water starts to decrease. Okay, so that's something important to keep in mind. Sugars are also have hydrocarbon groups, but they are able to dissolve. Sugars are able to dissolve in water. Now, they will not dissociate in water. They will not dissociate the positive and negative ions, but sugar molecules dissolve. And a lot of that has to do with the fact that sugars can make hydrogen bonds with water because they have OH groups. So you can form hydrogen bonds there. And that hydrogen bonding with the water will allow the sugar to dissolve, not to dissociate, but to dissolve. This is another picture showing methanol, so a very simple alcohol. So methanol, which is CH3OH, it can actually hydrogen bond with other methanol molecules. So you see one molecule here, and then another one here. And so this is hydrogen bonding occurring. And same thing here, you've got another molecule here. So that's hydrogen bonding occurring. Water obviously does hydrogen bonding. So if you mix methanol in water, then there can be hydrogen bonding attractive forces between a methanol molecule and water, but it will only happen between the OH group of the alcohol, like methanol, and water. It will not happen, you will not form hydrogen bonds between the non-polar part of the alcohol. So the longer the alcohol chain gets, the less likely that the hydrogen bonds will form, and if fewer hydrogen bonds form, the solubility of the alcohol in water will decrease. We talked about this a little bit in class. It is possible for you to have a polar molecule like acetone. So acetone is polar and it will interact with other acetone molecules through dipole-dipole interactions. But acetone will not hydrogen bond to itself. It can hydrogen bond to water. So here's the hydrogen bonding with the water. So you've got a bonded hydrogen on water, and it is attracted to the lone electron pairs on oxygen of this is propanone. Same thing as acetone. So there's your hydrogen bonding right there. Again, you've got a hydrogen sandwich between a bonded hydrogen that's bonded to oxygen, nitrogen, or fluorine. So hydrogen's in the middle, and then the bread part of the sandwich is this oxygen atom here that the hydrogen is directly bonded to, and then this oxygen atom up here. And that would be the attractive force, that hydrogen bonding attractive force. So if you want to talk about how polar solutes dissolve in polar solvents, an example would be formaldehyde. Okay, so that's going to be CH2O. That is a polar molecule. And then chloroform would be your polar solvent. So that is CHCl3. So that is polar. So what will happen is the intermolecular attractive forces between formaldehyde molecules is dipole-dipole. That is the same thing as between the chloroform molecules, dipole-dipole. When you mix formaldehyde with chloroform, since both your solute and your solvent both have dipole-dipole attractive forces, and the solute and the solvent can also interact through dipole-dipole attractive forces. And as long as the dipole-dipole between formaldehyde and chloroform is just as strong, if not stronger than formaldehyde, dipole-dipole, and chloroform, dipole-dipole, then that interaction between solute and solvent will cause the solute to dissolve. It will cause it to be soluble. Similarly, if you have non-polar solutes and non-polar solvents, dissolving will occur. So if you have I2 iodine, it's a non-polar molecule. So the only interactions between I2 molecules is London dispersion forces. So if I2 is placed in carbon tetrachloride, CCl4, which is also nonpolar, so it just has London dispersion forces, then the London dispersion forces formed between I2 and Cl4 will be similar, if not stronger than, the London dispersion forces between the solvent and the solute particles. So solubility, the substance will be soluble. Dissolving will occur. When you're talking about intermolecular forces and solubility, you want to make sure that you discuss the intermolecular forces between solute particles, solvent particles, and finally solute and solvent particles. You need this solute-solvent interaction to be just as strong, if not stronger, than both the solute interactions and the solvent interactions. If they are not, then dissolving will not occur. Okay, so what happens, back up. Okay, sorry. So what happens when you've got dissimilar intermolecular forces? So for instance, if you have a non-polar solute like CCl4 and you put it in a polar solvent like water. So let's imagine that this is CCl4. So it's nonpolar. So the only IMFs it would have would be London dispersion forces. Water, on the other hand, is polar. So water will have hydrogen bonding. So in the solute, I have LDFs. In the solvent, I have hydrogen bonding. The only way for the solute and the solvent to interact would be for the water to induce a dipole in the CCl4. Well, since dipole-induced dipole is not as strong as just hydrogen bonding, the nonpolar solvent is not able to break up, sorry, the nonpolar solute is not able to break up the polar solvent, which means the attractive forces between your solute, in this case CCl4, and your solvent, in this case water, those attractive forces will not be strong enough to disrupt the individual attractive forces in the solute or the solvent. So you will not get strong solute-solvent interaction. So dissolving will not occur. Okay, so now if we look at this, if we have a polar solute, or if you have an ionic solute, so like a salt like NaCl, and you put that into a non-polar solvent like CCl4, within the solute, you have attractive forces. So these are electrostatic, in this picture, positive ion, negative ion attractive forces. Those are strong attractive forces. In the nonpolar solvent, all you have is London dispersion forces. So if the solute and the solvent were to interact, then the ions would have to break up the London dispersion forces in the nonpolar solvent. That's not going to happen. So the attractive forces, an ion-induced dipole force, is not going to be stronger than an ion-ion attractive force. So an ionic compound will not dissolve in a non-polar solvent. In order for dissolving to occur, the solute-solvent interactions must be as strong or stronger than the individual solute-solute forces or solvent-solvent forces. And in this case, they're not. The solute-solute attractive forces are very strong. If the solute were able to interrupt the London dispersion forces, it would not be as strong of an attraction. So dissolving will not occur. So a favorable example of dissolving would be a polar solute or an ionic solute, as shown here, dissolving in a polar solvent like water. So here I have electrostatic attractions between positive and negative ions in the solute. In the solvent, I have hydrogen bonding between the water molecules. When solute-solvent interactions occur, they interact through ion-dipole attractive forces. So the negative end of water is attracted to the positive ion. So the water will surround and hydrate the positive ion. And similarly, the positive end, the hydrogen part of water, will be attracted to the negative ion. So the water will orient itself in that direction and hydrate the negative ion. Both of these are ion dipole attractive forces, which are as strong as your positive ion, negative ion attractive forces in the solute, and they're as strong as your hydrogen part. They're stronger than your hydrogen bonding in water. So this intermolecular force is strong enough to keep the solute and the solvent interacting and not going back towards a solid solute in liquid water. Okay, so we can also use solubility and intermolecular forces to talk about how to separate solutions that are made up of two or more different liquids. And one way to do that is through distillation. So distillation uses differences in boiling points, and differences in boiling points are ultimately caused by differences in the strength of intermolecular attractive forces. So the way this is going to work, an example is, so I have a mixture of water and ethanol. And so I would heat the water and ethanol. So water and ethanol not only can hydrogen bond to each other, but ethanol can hydrogen bond to other ethanol molecules, and water can hydrogen bond to other water molecules. Ethanol, because it is an alcohol, has both a polar and nonpolar end of the molecule. So the IMFs in ethanol are not quite as strong as they are in water. Water has hydrogen bonding, and that's a pretty strong intermolecular attractive force. So step one, if we heat this mixture, then the ethanol will evaporate. Its intermolecular forces are not as strong as water, so it will evaporate first. It's got a lower boiling point. It will evaporate first, and then we can send the evaporated ethanol down this cooling tube, cooling chamber of the distillation apparatus. So in this tube, there is water surrounding the tube on the outside. So it will cause any vapor to start to condense. So the ethanol vapor will start to condense, and it will appear in this distillate over here. Okay, so I've got ethanol molecules over here. I can then get a different beaker, and I can continue heating the water. So now water has a higher boiling point because its intermolecular forces of attraction are stronger. And then I can let the water condense in the condensation chamber, and it will cool, and it will be part of the other distillate. Okay, so that's one way to separate through the principles of intermolecular forces. Stronger IMFs have stronger boiling points, and therefore you can separate a mixture of water and ethanol based on the fact that each component will have a different boiling point. Ethanol boils at a lower temperature than water because its IMFs are weaker. Water boils at a higher temperature because its IMFs are stronger. Okay, and then the last type of technique that you could use to separate a mixture that's based on intermolecular forces and solubility is through chromatography. So chromatography is typically used to talk about paper chromatography. If you're separating within a dye different pigments that are in the dye, the different pigments that make up a dye may have different solubilities, so you can capitalize on that. So with paper chromatography, you're separating components based on their relative affinities, means how strongly attracted are they to the stationary phase, so how strongly attracted are pigments to the paper that they're on versus how strongly are they attracted to the solvent that's going to be used to move up the paper. So I'm going to skip this. This isn't important to what we're doing, but I will go back in just a minute. So if you have a chromatography setup, this would be a piece of filter paper. And then on the bottom of the filter paper, you would draw a line where you would spot different dyes. And the dyes could be made up of different pigments. And then you would prepare a mixture of a solvent. So it could be water, it could be alcohol. In this case, it's a mixture of water, which is polar, and isopropyl alcohol, rubbing alcohol, which for the most part is nonpolar. It does have a polar end, but for the most part it is nonpolar. And then you would let the solvent run up the paper until it gets to a certain point. And then you measure to see how far did each pigment run. So pigments, the paper, I'm going to go over here now. The paper cellulose is polar, okay? It contains hydroxide groups. So solutes or dyes that are polar are going to be attracted to the paper. Pigments that are not polar, they're not going to be attracted to the paper. They're going to be more attracted to the ethanol or to the isopropyl alcohol that tends to be more non-polar. So non-polar pigments, dyes, whatever, they will not move as high up. They will move higher up the paper because they're more attracted to the solvent, which is non-polar. Polar solutes are attracted to the paper because the paper is polar. So they won't move with the non-polar solvent. They'll stay on the paper. So you can separate out, if you have an unknown sample, you can separate the dyes in the unknown sample using chromatography. So this was given as the 2017 question that dealt with chromatography. So here you've got two different chromatograms. This is filter paper, and then you've got a solvent, and in this case the solvent is non-polar, and you have dotted in 3 locations dye A, dye B, and dye C. And then you've got an unknown dye, so you don't know what is in there. It could be a mixture of A, B, and C. So a student investigates dyes using chromatography paper. Student has samples of 3 pure dyes, A, B, and C, and an unknown sample that contains 1 of the 3 dyes. The student prepares the chromatography chambers as shown above on the left by putting a drop of each dye at the indicated position on the chromatography paper. And they're telling you that the chromatography paper is polar. So if the dye is also polar, it will stick to that polar paper. And they're putting that chromatography paper into a non-polar solvent. So if the dye is more non-polar, it's more attracted to the solvent, so it will move up the paper more. So question A, which dye, A, B, or C, is the least polar? And justify your answer, between the dyes. Justify your answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. So once the chromatogram runs, you let the solvent run up to this point. And what you can see is that dye B is the most polar because the paper is polar. And so if the dye or the solute is very attracted to the polar paper, it probably has similar INFs, probably also polar, so it's going to stay attracted to the paper. Whereas dye C moves up higher in the paper, so it is less attracted to the paper and more attracted to the solvent. Okay, so dye C is the least polar, dye B is the most polar. Second question, which dye is present in the unknown sample, and justify your answer. Okay, here's what I remember in 2017, my students came in and they were concerned about this. What you need to notice is that the solvent has not moved the same distance in the original dye sample and the unknown sample. So if you will look in the original sample, dye A is about in the middle of the chromatogram. So it has migrated about halfway up the paper compared to how far the solvent has moved. In the unknown sample, the unknown has migrated about halfway up the paper based on where the solvent stops. So dye A is most likely to be the unknown because each spot has migrated about halfway up the paper compared to how far the solvent has moved. So they probably had similar intermolecular attractive forces, and their dye A is the unknown. So I'll let you see the, oops, there you go, the actual answers, and I'll pause a minute so you can read that. And so that's the rest of the 9.3 notes, okay? So I'll do a separate recording for how to answer some practice FRQs, and that will be next.